Okay, so in this video we will talk about EEG brainwave signal classification. This presentation will provide an in-depth overview of the classification of EEG signals, crucial technique in neuroscience and biomedical engineering, by examining different brainwave bands, pre-processing method, feature extraction techniques, and classification algorithms. This presentation will highlight the significance of EEG in understanding brain activity and its application in medical and cognitive research. Now, introduction. Uh, Electroencephalography (EEG) is a non-invasive technique that measures the electrical activity generated by the brain's neurons. By placing electrodes on the scalp, EEG captures voltage fluctuations resulting from the ionic current flows within the neurons of the brain. This technique has been widely used for diagnosing neurological disorders, monitoring cognitive states, and researching brain functions. The primary advantages of EEG is its high temporal resolution, making it ideal for capturing real-time brain activities. However, it has low spatial resolution compared to other neuroimaging techniques like fMRI. Which is applied in various domains in medical diagnostics such as epilepsy monitoring to research in sleep stages and neurofeedback therapies. Recently, it has become an essential component in brain-computer interface systems, enabling direct communication between brain and external devices, which has transformative implications for assistive technology in neurohospitals. EEG brainwave bands. EEG signals are classified into different frequency bands, each associated with specific brain states. The primary brainwave categories include delta waves, number first, 0.5 to 4 hertz. Okay. These low frequency waves dominate during deep sleep and restorative states. High levels of delta waves are common in newborns and during deep state of non-REM sleep. Second is theta waves, which are linked to light sleep, drowsiness, meditation, and they also play a role in movement, cooling, and terror. Third one is alpha waves, 8 to 13 hertz. This imply a relaxed state, alert state. They are most common when a person is in a calm, reflective mood, often with closed eyes. Beta waves. Beta waves are associated with active thinking, focus, and mental engagement. They dominate during cognitive tasks and problem solving. Gamma waves are high frequency waves which are due to complex information processing, sensory perception, and high level cognitive function. Uh, so, Also, understanding the frequency bands helps in identifying and classifying different mental and cognitive states based on EEG developments. Now, moving further, we'll talk about EEG signal acquisition and preprocessing. In signal acquisition, this is the main process where the electrodes are here. You can see in the picture electrodes are placed on the 1020 system. uh, Actually, the 1020 placement scheme is most widely used, and each electrode captures signals from the underlying cortical areas, providing insights into localized brain activity. However, the raw EEG data is often noisy and requires extensive pre-processing. So, after signal acquisition, we go on pre-processing. The main pre-processing techniques are noise removal, signal normalization, and then segmentation. So in noise removal, basically we remove the noise using band pass filtering and independent component analysis techniques. And the EG signals are like other signals are of course prone to noise from muscle movements, eye blinks, and external electrical interference. That's why it is an important factor. Now, signal normalization ensures that the signals are on the same scale, which is crucial for comparison and classification. And then we do segmentation, which basically EEG data is typically divided into smaller time windows for feature extraction and analysis. And then yeah, feature extraction using short-term Fourier transform and linear transform. Now let's talk about feature extraction for classification. And there are three main techniques: time domain, three main features: time domain, frequency domain, and time frequency analysis techniques. No, time-domain features. Metrics like mean, variance, skewness, and kurtosis are derived directly from raw EEG signal and capture the statistical properties of the data. And in frequency domain features, techniques such as power spectral density analysis helps identify the power distribution across different frequency bands. This is crucial for identifying the dominant domain activities. And in time frequency analysis, methods like short-term Fourier transform and Weber transform allow simultaneous analysis in both time and frequency domains, making them effective for capturing transient features in non-stationary EEG data. Classification techniques. After the features are extracted, we do classification uh, using traditional ML methods, and now mostly we using deep learning methods. The traditional methods we used were support vector machines, which are effective for binary classification tasks and work well with high-dimensional data. And random forest, which is an in-symbol method robust to overfitting and works well for multi-class problems. And k-nearest neighbor, of course, which is simple and effective for small data sets but can be computationally intensive for large data sets. Now, deep learning models. CNNs automatically learn special patterns in EEG data and are often used for sleep stage classification and long short-term memory networks, LSTMs, which capture temporal dependencies in sequential EEG data, making them suitable for dynamic state. So basically LSTMs are currently the best for classifying EEG data. Now, uh, each technique has its advantage and is chosen based on the nature of classification task. Now we'll talk about case study, uh, an important case study, which is brain-computer interface applications, prominent application of EEG. In a typical BCI setup, the user performs specific mental tasks like imaging left or right hand movement, which are captured as EEG patterns and classified by the system. For instance, modern imaging classification using CNNs, which is promising for person limbs. The performance is measured using FN score and specificity and sensitivity, which indicates how well the system distinguishes between different mental tasks. Now, challenges and limitations. uh, See, there are many challenges. Main are listed here, like low signal to noise ratio and large data set requirements and high variability. Basically, high variability basically means that the EEG signals are highly variable both within and across the subjects, making classification difficult. And again, they are susceptible to noise like any other signal. And large data set requirements is a new problem because we are now using deep learning models which require huge amount of data. Like ML models, they didn't require that much data, but since deep learning models are much better, we are using them which require a lot of data. So yeah, hospitals would be useful. Future directions. Uh, Improved signal acquisition, which has been like quite important for portable EEG devices, and which helps in bettering spatial resolution and advanced modeling techniques. We are like looking for hybrid models of fMRI and eye tracking, which has been comprehensive in brain state analysis and transfer learning, which is quite new, and researchers are like still learning on the subject, and it is helping cross subject classification without need of large label data sets. Actually, large level data sets are not like labeled data sets are not also required for deep learning, but yeah, transfer learning has been useful in this. Now, conclusion. EGP in wave classification is a pivotal tool in understanding brain function and developing neuro technologies by leveraging advanced processing, face extraction, classification techniques. Researchers can decode complex brain states and develop neural applications from cognitive research to BCI systems. And thank you.